Okay, so far the proofs that we've been doing in monadic predicate logic have pretty much been following the rules that we were given in propositional logic. And we've just been doing um, kind of direct derivations so far, but you can also do conditional and indirect proofs in monadic predicate logic, and that'll be really useful in a lot of ways. But there's one important thing to remember. There's one crucial difference between doing indirect proofs in predicate logic compared to propositional logic. So, and I'll explain the rule in some more detail, but basically the rule is within the scope of an assumption, inside of an assumption, for either a conditional or an indirect proof, you can never universally generalize on a free variable. Normally, if we have something like Rx somewhere in the is one of our premises in a proof, we could go ahead and universally generalize to for all x's are x. But inside the scope of an assumption, either conditional or an indirect assumption, we can never universally generalize. Very important to remember. So here's an example of a situation. We see for if it's true that for all x is sx, then for all x is ix. And we're going to go ahead and use conditional proof here. So in premise 2, we assume sx. In premise 3, we make a mistake here when we universally generalize. We can go ahead and assume sx, but we can't universally generalize inside the scope of the proof. Now, one of the reasons for this is that, well, normally when we have just floating variables, that's because we instantiated some universal claim. So they're able to maintain their universal character, and we can universally generalize from free variables because they were instantiated from universals in the first place. Now, if we think about what a free variable like this is, sx, all that sx is saying is s. It's an incomplete sentence. It doesn't have either a quantifier or a specific object that it refers to. So by itself, it's just kind of incomplete. So when we assume a variable, we need to treat this variable, even though it's a variable, as existential in a certain way. The assumption with sx is that there's just like some random object that has the property s. It doesn't retain its universal character of applying to all objects. And that's because it's just an assumption that we're making about sx. Here, we're saying that there's some object s. It's not something that we instantiated from a universal statement in the first place, and so we can't universally generalize from it. Now, of course, we can assume for all x's sx, and we can universally instantiate inside the scope of our quantifier or of our conditional proof in this case and go from there. But in that may or not be helpful to us, and it's not going to accomplish the same thing that we see here with this example of doing it badly. Whether you understand exactly what's going on or not, and I'll try to explain it a little bit more because it is important that you understand. The most important thing is if you can remember, never universally generalize within the scope of an assumption, you're set. If you can follow all the other rules and you remember to never universally generalize inside the scope of an assumption, then you'll be fine. That's the important thing to remember with conditional and indirect proofs in monadic predicate logic. Now, of course, once you discharge the assumption, you can, if you have some variables that you're working with, so like for example, once we've discharged, so this doesn't work anyway, but for the sake of the argument, we've discharged if sx then ix. We're now outside the conditional proof, so there's no problem with universally generalizing at that point. All right, so yeah, so there's some problem. You run into some issues if you universally generalize. So in this case, we're going from if it's true that for all x is sx, then it's true that for all x is ix. And that's different than saying, well, for all x's, if sx, then ix. So from if everything is s, then everything is I, we have inferred every s is I. So that relationship doesn't follow from the initial statement. So let's give a more concrete example. If we take S to stand for substance and I to stand for incorruptible, we have moved from if everything is substance, then everything is incorruptible, to every substance is incorruptible. Now, we're talking about two different things in each of these sentences, and intuitively it's clear that they're not equivalent to one another. So that's the important thing to remember. Never universally generalize within the scope of an assumption. We will have floating variables in the scope of an assumption, but we can't jump up to a universal statement from there. Floating variables are a little weird in the first place because they're the only they're something that we will instantiate with variables to make universal claims more easier to work with. And they have a universal character only insofar as they come from a universal statement in the first place, and they don't if it's just an assumption that we're making. All right, so well, let's do some examples. So here, our first premise is for all x's, if px, then bx. And our second premise is for all x's, if bx, then rx. And the conclusion that we want to show is if there is at least one thing px, then there is at least one thing rx. So because our conclusion is a conditional here, this is a pretty good, it's a pretty good way to start this proof would be just to assume the antecedents of the conditional, see if you can get to the consequent using a conditional proof, and then if you can, then you can discharge the conditional statement that we get, where we assume if there is at least one thing that has the property P, and then we can arrive at there is at least one thing that has the property R, well, then it's true that the relationship between if there is at least one thing P, then there is at least one thing R holds, so we can discharge that conditional statement where the antecedent is the first line of our conditional proof, or our assumption, and our consequent is the last line of the subproof. So we'll go ahead and assume the antecedent and see if we can get to the consequent. Remember, we're going to indent here to make it clear that we're working with a subproof. The next step that we'll want to do is existentially instantiate premise 3. We can see that premise 1 and premise 2 are both universally quantified formulas, so we can instantiate those using the same constant or constants that have already appeared in the proof. But remember, for existential instantiation, you have to use a new constant that hasn't appeared in the proof yet. So if we want all of this stuff to work together, we have to existentially instantiate before we do our universal instantiation. So we know there is at least one x px from line 3. We go ahead and existentially instantiate from there. So we get one thing A that has the property P. We'll go ahead and universally instantiate line 1 using the same constant so that everything is commensurate. So we get if A is P, then A is B. We'll do the same thing for premise 2 as well. We get if A is B, then A is R. So now, because we have this, we see that, well, if A is P, then A is B, and if A is B, then A is R, well, we can use hypothetical syllogism to cut the middleman out of that chain of conditional statements and just get to if A is P, then A is R. That's from lines 5 and 6, hypothetical syllogism. Now we can use modus ponens with line 4 and line 7. We know that if A is P, then A is R, and we know from line 4 that A is P. So then we get to A is R from lines 4 and 7 modus ponens. Now we can existentially generalize. Remember, we can't universally generalize, but existential generalization, that's okay. So we'll go in and existentially generalize from there. And now we can discharge our entire conclusion, because the first line that we had, we started with the antecedent that we needed, and we arrived at the consequent that we needed. So we discharge the entire thing as this conditional statement, where the antecedent is the first line of our conditional proof, and the consequent is the last line of our conditional proof, and as justification we write lines 3 through 9, conditional proof, and because this matches our conclusion, we're done. All right. We'll do another one here. So here we can see there is a conditional statement in our conclusion, but the conditional statement isn't the major operator of the conclusion, it's the universal quantifier. So let's look at our premises. Our first premise is for all x's, either not cx or dx. Our second premise is it's not the case that there is at least one x not dx if and only if tx. And our conclusion is for all x's, if cx, then tx. So we can see, well, line 2 would be pretty easy to use quantifier exchange on, make that a universal statement that makes it in line with everything else. But it looks like we can't just start with the entire antecedent of a conclusion that we wanted to, like in the previous one. But we know that, well, part of the conclusion that we want to show is a conditional statement. So we can arrive at that, and then if we can discharge if cx then tx, then once we're outside of the conditional proof, then we can universally generalize from there. So we'll go ahead and assume this portion of the conditional statement that's in our conclusion. We'll assume cx for our conditional proof. We'll go ahead and universally instantiate line 1 to keep things commensurate with each other. And because we want to, when we discharge this, we want these to be variables so that we can then universally generalize. Now, we can't do any sort of instantiation with premise 2 as it is, so we'll have to use quantifier exchange on it to make that usable. But first we're going to get some material here. So if we have cx on line 3, and from line 4 we know that either not cx or dx, and we know that it's not the case that not cx from line 3, we go ahead and double negate that. Then we can arrive at dx by itself with 4 and 5, disjunctive syllogism. Now we'll go ahead and use quantifier exchange on line 2, where we get for all x's, dx if and only if tx. We can universally instantiate that, which will allow us to keep using these variables that makes all this stuff work together. So here the slide gives an example where we're using a biconditional rule. We didn't go over any of the biconditional rules, so we would have to go ahead and use material implication to change that biconditional into, in this case, it would be the easiest to turn it into a conjunction of two conditional statements. Use simplification to get the first of those conditional statements, which will be if dx then tx. And then we use modus ponens on that to get tx, but either way we get to tx, and this keeps everything on one slide. And so now, since we arrived at tx, we can go ahead and discharge. So we get if cx then tx, and we show that from 3 through 9 conditional proof. And now we're outside of the assumption for the conditional proof, so we can universally generalize over this conditional, which gives us the conclusion that we're looking to show. All right, this time let's do an example with an indirect proof. Remember, so for a conditional proof, what we discharge is a conditional statement that expresses something about the relationship between the first line and the last line, where if the first line is true, then the last line is going to be true, and that's true because we were able to derive the last line assuming the first line. But with an indirect proof, what we want to do is assume something and see if we can generate a contradiction. If we can generate a contradiction, then we know that our initial assumption can't be the case, so we discharge the negation of that assumption. So Our first premise here is for all x's, if sx, then px. And our second premise is there is at least one x, sx. And we want to show there is at least one x, px. So because our conclusion is there is at least one x, px, and an indirect proof gives us the negation of our assumption, if we take the negation of our conclusion as what we want to show, then we'll discharge the conclusion double negated, and then we can just apply double negation to it, and we'll have our conclusion. So we assume it's not the case that there is at least one x, px. We can go ahead and use quantifier exchange on line 3 here. So if it's not the case that there is at least one x, px, that means that for all objects, it is not the case that they have property p. If it's not the case that even one object has property p, that's equivalent to saying for all objects, it is not the case that they have property p. So line 4, we get this universally quantified formula using quantifier exchange. Now we can go ahead and start instantiating stuff. Remember, we have to instantiate premise 2 first because this is our existentially quantified formula. And whenever we instantiate an existentially quantified formula, we have to use a new constant, which is a restriction that we don't have with these other universally quantified formulas that we're using. So now we'll go ahead and do universal instantiation for premise 4. And we'll go ahead and universally instantiate premise 1. And we're going to be using the same constant in all cases, so things will just work together. Now you can see already that it'll be really easy for us to get a contradiction from here. We know that if SA, then PA, so we can get PA, and then we have PA and not PA, or we can use modus tollens to get not SA with line 6 and 7. Then we'll have SA and not SA on the same line. We can go either way here. So here we'll go ahead and get PA with modus ponens, lines 5 and 7. If SA, then PA, and we do have SA, so it's true that we have PA according to what we've been given. So now we'll go ahead and use conjunction on lines 6 and 8 to get PA and not PA on the same line, make it real clear that we have a contradiction. Now that we have our contradiction, we can go ahead and discharge the first line of our indirect proof, which in this case was, it's not the case that there is at least one x, px. And when we discharge it, we add a negation to it. So we get, it is not the case that it is not the case that there is at least one x, px. And our justification is lines 3 through 9, indirect proof. So not quite done. We have one more step. Now we can use double negation to get rid of those two tildes. And on line 7, we have the conclusion that we were looking to show. Okay, so those are some examples of conditional proofs and indirect proofs in predicate logic, monadic predicate logic. It works the same way as it did before, with just one extra rule to remember is that you never universally generalize within the scope of an assumption. If you can remember to never universally generalize within the scope of an assumption, everything else works pretty much the same way. We have some other rules going on, like quantifier exchange, instantiations, generalizations, etc. But with all those tools and remembering that you never universally generalize within the scope of an assumption, I'm saying it a lot because it's easy to forget, then you should be set. Again, if you have any questions or would like to see more examples, feel free to send me an email. And hopefully when I do the homework solutions videos showing you working through the homework problems, that should help clear anything up. But if it doesn't, feel free to contact me and I'm happy to help with anything that you're stuck on.